Welcome everyone to the Western Museum of Flight. I'm Cindy Maka, the director. For those of you who have seen the F-35 make its very impressive vertical landing on a Navy ship, you are about to hear the story of how this came to pass by the one man whose work was indispensable for bringing it about. For those of you who have not seen this demonstration, you are going to want to after today's talk. It's my privilege to introduce Dr. Paul Bevilaqua.
Well, thank you, Cindy. You know, when they asked me to give this presentation, I asked them, well, how long have I got? And they said, well, we like to keep it under 45 minutes. And that reminded me of something my daughter said when we first came to California. She was about 5 years old at the time. And the guys at work said, you have to go for a drive in the wine country in the hills behind Santa Barbara, where Michael Jackson and Ronald Reagan and Kelly Johnson, who founded the Skunk Works, had these Hollywood ranchettes. So we're driving down this two-lane country road, and she sees one of those oil wells that looks like a dipping bird. She said, Mommy, what is that thing? Marilyn says, well, why don't you ask your daddy? He's an engineer. And she says, no, I don't want to know that much about it. You've had the experience too, huh? Well, anyway, these are the three airplanes that the Joint Strike Fighter was designed to replace. They were all designed around the same time in the 1970 era, and they all had the same shortcoming. They weren't stealthy and they didn't have enough range. And in the case of the Harrier, it wasn't supersonic. And so the program actually started with the Marines, who were looking for a supersonic replacement for the Harrier. The Marines are an expeditionary force, which means they go ashore without heavy artillery. They used to rely on battleships for artillery support, and then it switched to carrier-based aircraft, which provide close air support. But in Guadalcanal, the Japanese fleet came down and the battleships pulled back 400 miles because we only had two left after Midway and Coral Sea, and they were left without air cover, and they were bombed and strafed for a month severely while they were trying to get the air base that the Japanese had started to build finished until they got the Cactus Air Force on board. So every Marine knew why they needed an airplane to come ashore with them that wasn't dependent on the carrier. But the Harrier was an interim solution because it provided the close air support, but it wasn't supersonic, so it couldn't provide top cover. So they needed the F-18s, carrier-based, to provide top cover so the Harrier could provide the close air support. And that still tied them to the carriers. So they wanted something that would eliminate that constraint. And here's the reason the Harrier isn't supersonic. These two airplanes were also designed in the 1970s. The F-104 had 15,000 pounds of thrust, and it went Mach 2, and the Harrier with 20,000 pounds of thrust could only go Mach 0.85. And this view shows the problem. When you go supersonic, you need a long, slender airplane, and to go vertical, you need a helicopter stuffed inside your airplane. And so the Harrier has a huge lift fan, which prevents it from being long and slender, and therefore from being supersonic. And here's the problem. You can increase thrust by increasing the mass flow or the velocity. And if we look at the index of the thrust per horsepower, which is m dot v thrust over 1/2 mv squared power, and do a little math, we find that you get maximum thrust per horsepower when you have maximum airflow. So a large mass flow of air at low velocity is a lot more efficient than a small mass flow at high velocity. And that's why helicopters are more efficient in hover than rockets, and why the Harrier needed that huge airflow. Well, I had been working for North American on the XFV-12A, which was Admiral Zumwalt's idea for solving the problem of the backfire missiles, backfire bombers that would launch cruise missiles onto the carrier. They would stand off 300 miles and launch the cruise missiles. So his idea was to put a picket ship out in front of the carrier battle group and have a short-range VSTOL airplane that could take off and intercept the backfires before they could get close enough to launch their missiles. So we worked on that program. But when Admiral Zumwalt retired, they recognized that this was a ill-posed mission. First of all, the backfires could come off over in the morning, take out the picket ships, come back in the afternoon, get the carriers. But the point was the carriers at that time didn't have a nuclear capability. And so the Navy submarines provided the nuclear response of the triad. And so they canceled the program. And I was without a program and came to Rockwell at that point. And the guys from the Navy came to me and said, look, the Marines are looking for a supersonic replacement for the Harrier. They don't need a lot of range. How about seeing if you can adapt this airplane? So I was new in the Skunk works. I brainstormed with the Skunks, and we came up with a bunch of concepts, and then we do the literature search and patent searches, find out someone had thought about it, already built one in many cases, and they didn't work. So I had to look into how you solve problems. And basically what the psychologists say is our minds work by analogy. So the atom is like a solar system with a nucleus like the sun, and then the atoms in orbit around it. An electric current is like a river. It flows against the resistance driven by pressure, which is the voltage. And so the basic approach for problem solving is you find a similar problem with a known solution, and you use the analogous problem for your solution. And the classic example is the Wright brothers themselves. Wilbur Wright was standing in their bicycle shop idly twisting the cardboard box that the inner tubes came in, and he realized that if he twisted it, one side would go up, the other side would go down, which is just what you needed to bank into a turn. And on the right side there is their patent, which basically uses that concept. A more recent example is the F-117. So the first helicopters we sent to Vietnam had bubble canopies, and a bubble canopy is sort of like a disco ball. You put a light on it, and wherever you are, there's a point on the canopy, on the disco ball, where there's a spot of light that will go to all over the room. So we were flying our helicopters below the radar, down river valleys, but the VC could get up on a hillside, look down into the valley, and see this helicopter and track it by the image of the sun. So the first helicopters designed specifically for Vietnam didn't have bubble canopies, they had flat panels. So there was one angle of incidence at one point where if the guy happened to be in the right spot at the right time, he'd see a glint, but then the helicopter would move and he couldn't see it anymore. And Dennis Overholzer, who was an avionics engineer in the Skunk works, was familiar with the electromagnetic spectrum. There's the visible light in the center there. To the left of it is infrared, and to the left of that is microwaves, and then longer and longer wave radars. And so he said, to first order, radar is going to reflect like the light does. So the vice president of engineering at the California company sent Dick Shearer over because the Skunk works were trying to make the SR-71 stealthier. And they had been told by the Air Force that it wasn't going to work. They weren't reaching anywhere near the signatures. So Richard asked Dennis, what's the ideal shape? And he said, well, a pyramid is, because you have a flat bottom, and you can see the radar waves are reflected away, and the pyramids on the side are reflected up and away, and there's no return back to the signal. And the guys working the SR-71 variant call it the hopeless diamond, because there's no way you could make a pyramid fly. But Dennis figured it out. He stretched it out like a kite, added some wings, and came up with the F-117, and that's what the F-117 looks like on a radar. There's a fuzzball, which is small due to all the intersections and panels and doors and access panels, and it spikes in a few directions. So if you happen to be in a radar at that location where you hit a spike, you'll see the spike, but then the airplane disappears. So essentially it works just like the helicopters did. So we work by analogy. That's why they gave us those tests in the 7th grade where you had a bunch of objects and they said which one is similar to the others and which are different. And so this is the hardest question I found. Which three things have something in common? I'll give you a second to look at it. And the answer is it's the airplane, the frying pan, and the watch, because they're both all made out of metal. So, for those of us who weren't geniuses, there are techniques that have been designed to help with that. One of them is to say, how did someone else solve the problem? So there's a weightlifter who takes a brute force approach, like direct lift Harriers. There's Iron Man who has jets coming out of his legs and feet, 4 posts. And there's a magician who makes his airplane appear to hover, appear to float, but it doesn't really. It's a trick. And there have been some airplanes like that that have been proposed. The Russians actually tried to systemize it, as they want to do. When the wall came down, they sold the system called TRIZ, which stands for something in Russian like technical research involving systems. And they made a list of all the physical systems that they could think of. And this is a page from that TRIZ manual in which they tried to systematize this problem solving by analogy. So the idea is you would go through your problem, go through the book and find something similar and find the analogous solution. I tried reverse engineering the Joint Strike Fighter with the TRIZ system, and it didn't work for me. But the method that did work is a method of forced associations. You state the problem, and the problem was that the Marines wanted a Harrier or a F-18 that could land vertically, and the problem with the F-18 is that it's got doesn't have enough thrust and it's too far aft. So the nominal takeoff weight of an F-18 is around 37,000 pounds. Dry thrust is 22,000 pounds. Whoops. And so you need essentially to double the dry thrust and move it forward of the CG to balance the airplane and hover. So the trick is then you identify the steps required to obtain a solution, extract power from the engine, transfer the power to the front of the airplane and turn it into thrust. And you brainstorm those steps. So how can you extract power from a hot, high-pressure gas? With turbines or scoops, heat pipes, alternators or generators, generate electric current, putting ions into the jet and passing it through a superconducting magnet, getting magnetohydrodynamic or electrofluid dynamic forces, lasers, you could use it to pump a laser, work some chemistry, and then how can you transfer power from the back of the airplane to the front? You conduct it, the mechanical drives, beam it, wires, electrical fibers, hydraulics, etc. And then how can you produce thrust? Afterburning, ejectors, fans, pulse jets, rockets, rotors, reverse the MHD, EFD, or chemistry, and produce thrust out of it. And the technique is to pick one from column A, one from column B at random and see if you could come up with something. So we did that, and here's an example of an innovative system we came up with. You use the gas to pump a laser, gas dynamic laser. You beam the energy to the front of the airplane, focus it on the air, superheat the air, it explodes and causes pulse jets. So we came up with innovative solutions, but not very practical. And I had a 9-month contract from the Marines and DARPA to come up with something. I'd spent 8 months figuring out that we didn't have any ideas that would work. And I had a final report to write. So I sat down and I said, well, the best way to get power out of a hot, high-pressure gas is the way we've always done it, with a turbine. And the best way to get power forward is with a shaft. It's small, it's round, it doesn't add anything to the external diameter of the aircraft, and the best way to turn the power into thrust is the way we do it in the Harrier. You need a lot of mass flow at a low velocity, so that's a fan. And that became the basic systems. So we have a shaft driving a lift fan in the front, and you vector the nozzle in the rear. And that gives us a means of pitch control, because you can vary the thrust front to rear, and roll control, because you can vector to the, or yaw control, because you can vector side to side, but you need roll control. And I thought, well, I'll take the fan air and duct it off to the wingtips for roll control. But that created a problem, because the nozzle is sized for all the mass flow, and now it's taking some of the mass flow off, so the nozzle was oversized. The pressure drop through the nozzle would decrease, or the pressure drop through the turbines would increase, the turbines would spin faster, and the engine would blow up. But I thought, wait a minute, that's exactly what I want. I want something that will produce more power, and then I can absorb it to drive the lift fan. So like a car engine, you put it in neutral, step on the gas. If there's no rev limiter, the engine will speed up till it blows up, and I had an MG that did that on me. But if you put it in gear and let out the clutch, you put the energy into accelerating the car instead of the motor, and you don't blow up the engine, and you get the extra power out of it. So that became the basic concept for the Joint Strike Fighter propulsion system. About 10 years ago, Aviation Week was doing an article on innovation in aerospace, and they cited the propulsion system as an example of a recent innovation. And the next week, some wise guy wrote a letter to the editor and said, "You got an engine driving a fan. That's pretty obvious, isn't it? What's so innovative about that?" So let me go into a little more detail about what's so innovative. Before the Joint Strike Fighter, there are two kinds of turbine engines. Turbofan engines, or jet engines, which produce jet thrust but no shaft power. And turboshaft engines, like in locomotives and steam and ships. There was a turbine car that Chrysler built. Hospitals use them for power and emergencies that produce shaft power but no jet thrust. This is a simple concept of the difference between them. In a turbofan engine, you pass the flow through a compressor and then add heat to burn energy, add energy from heat. Then you take a turbine that extracts enough power to run the fan, and then what's left you squirt through a nozzle to produce thrust. So the engine companies refer to everything upstream of the nozzle as a gas generator, because its purpose is like a rocket engine to produce hot, high-pressure gas that you can squirt through a nozzle. If you go to a turboshaft engine, you put in one or more additional turbine stages, extract that power, you have nothing left in the exhaust, but you now have shaft power. I didn't want to go through turbine TS diagrams and thermodynamics for the generals and admirals and the staffers that I would have to brief, so I created what I call a TX diagram. So this is what happens to the energy of the flow as it goes through the engine. Initially, you add work of compression, then you burn the fuel and you get the heat addition. Then you take the power out from the turbine to run, with the turbine to run the fan, the compressor and fans, and then what's left you squirt through the nozzle, and unfortunately you have some waste heat when you're done extracting the power. And here's how it works really. There's a conventional operating line where the cruise point is maximum efficiency, and then as you throttle back you come down in efficiency, but you go through a point of maximum efficiency at every speed, every RPM. But the engine will run off design, and it can move to the hover point there, where you get an additional 25,000 or so shaft horsepower. The efficiency drops from 99% to 95%, so you lose 4% in efficiency, but you're only hovering for at most a minute in a whole mission, so that's a small price to pay to get enough power out of it to run the lift fan. And so that's what it looks like in our system. It's a dual cycle system. When we're in cruise mode, we're extracting power from the turbines to run the compressors, but when we go to the lift fan, vertical mode, we extract additional power to run the lift fan and leave less power in the nozzle. So what it looks like from outside the airplane is you've taken some of the power at the back and some of the thrust at the back and moved it to the front of the airplane. Here's the equation. The turbine power equation is right up there with F equals ma. It's m dot c sub p delta t, where delta t is the turbine drop, the pressure temperature drop across the turbine sections. T04 is upstream, T05 is downstream. If you factor the T04 out, you get a temperature ratio, which you can use the isentropic flow equations to turn into a pressure ratio. So T04 is the way we normally throttle an engine. We burn more fuel, raise the temperature, the turbine speeds up until the compressor absorbs the additional power. The engine's turning at a higher speed, pumping more air, producing more thrust. But you can also do the same thing by changing the pressure ratio, and that's what we do on the Joint Strike Fighter. So here's a PX diagram. So you raise the pressure through the compressor stages, you burn at constant pressure, and then you come back to atmospheric pressure through two turbine stages, the turbine pressure drop and the nozzle pressure drop. Normally we think of the turbine as a series of blades that are developing lift, but you can look at the channel between the blades as a nozzle by Newton's law, action and reaction, and that's similar to those sprinklers with the hooks on the end that swirl around and produce rotational motion to water the lawn. So when you open the nozzle up or extract the bypass air to run the roll jets, you reduce the pressure drop across the nozzle, so you have to have a greater pressure drop across the turbine. It's working harder, and that's where it gets the more power to run the lift fan. So I'll show you that again. There's the cruise mode, and there's the vertical mode. So it's dual cycle. So I had a solution for my DARPA report. The time in F-117 was what a stealth aircraft looked like. So this is the original sketch of the Joint Strike Fighter that I submitted to DARPA and the Marines. The F-119 engine was said to be a supercruise engine. It was near stoichiometric, no oxygen left, so there was no need for an afterburner, and so I distributed the flow at the trailing edge, and I had the fan in line with the lift fan in line with the engine, just like the Harrier, and used Harrier-type vectoring nozzles. Well, the Marines liked the concept. DARPA thought it was DARPA hard, so they wanted to give us a contract not to do a sketch, but to do a real conceptual design study, and they didn't want to go publicly with it, so they gave a contract to McDonnell Douglas, who was working with NASA on the Advanced Oval program, which wasn't stealthy, and had built the F-15s, and General Dynamics, who had built the F-16s, was also working with NASA on the Oval program. And the three of us got black contracts to do the conceptual design study. So let me say something about the Skunk Works and the way we operate. The Pareto principle is the 80-20 rule. Pareto was an Italian civil engineer, and he did a study of his business, and he found that 20% of his clients were producing 80% of his profits. And he had a garden out back, and he found that 20% of the plants were producing 80% of the vegetables. And he looked at land ownership in Europe, and 20% of the people owned 80% of the land. So he published a paper on that called the 80-20 rule, the principle. And here is a series of examples from more recent times from Norm Augustine's book. You've probably heard of Augustine's laws. So he's got the, let's see, the salaries of ball players as a function of their batting average, the inertial accuracy of guidance systems, diamond carats, machine part fineness of their finish, radar availability, and they all follow that 80-20 rule. So you get 80% of the performance for 20%, you get 80% of the performance for 20% of the cost, and those little blue triangles are the airplanes. So there's the three airplanes, and the F-16 at Mach 2 is down there at the low end, and the SR-71 at Mach 3 plus is at the high end. And so the Skunk Works approach is you do a little bit of a study to make sure you haven't got a bad concept. If you're doing something like we do in the Skunk Works, which has never been done before, you're going to be surprised by something anyway. So don't try to optimize, because you're just optimizing your ignorance. Build a prototype as quick as you can and get to find out what the real problems are and solve those. And in fact, it doesn't really matter. Now here's two airplanes designed at the same time for the same mission, nuclear bombers, similar ranges, similar payloads, but the wing areas are completely different. Therefore, the lift and drag coefficients are the same, but look at the bottom line of the cruise L/D. Doesn't matter. So you pick one, doesn't matter which one, you can optimize them and tweak them, but pick one, get on with it, test it, find out what the real problems are and solve those. So the golden rule in the Skunk Works is to get to a prototype fast. And Kelly used to say a good design tested now is better than a perfect optimized design tested next year. Now the DARPA and the Marines were very special, and they were great to work with. The Marines didn't have any money, and DARPA was looking for innovation. So typically you would get a set of requirements from your customer. So in this case, an airplane that goes Mach 1.5 and has 7.5 Gs, and your job then is to design the lightest airplane that can meet those requirements. But they said, we don't know what the requirements are for a stealthy, supersonic, STOVL strike fighter. The F-117, although it has an F designation, is not a bomber or a fighter, it's a bomber. It doesn't have air defense, guns, missiles, or anything. It's just a bomber. So you can get the same degree of survivability by either having a slow-speed airplane with a highly maneuverable that could jink and avoid being hit like a wild weasel, Or you could have a hypersonic airplane that comes over so fast they can't get their pants on in time to get a shot off at you. And they didn't know where that optimum place was. So they said, what we do know is what we can afford. We can afford an F-18. We'll give you 5% margin for stealth and anything else with the VSTOL. And you tell us where you fit on the design line between G's, Mach number, speed, range, payload, etc. And if we like it, we buy it, and if we don't, we won't. So between the F-117 and that then, which was 10 years before this airplane, the computers became more powerful, and we didn't have to analyze big facets using those Russian equations, but we could put thousands of little facets on there, like a Pan Air program, and analyze the signature. So I'm going to show you two versions of the signature of a generic airplane. Blue is low signature, and red is high signature. Oh, there it is, okay. So there's a generic kind of airplane, and it's blue in front and blue in back. So he won't see you if you're coming head to head. And if he gets ground control intercept on your 6, his IR and radar guided missiles can't see the airplane. But if you're going on the side of the airplane, you're going to see it. And wild weasels, in fact, used to fly over the SAM sites and draw the missile attack and then jink away from them. So hitting an airplane from the side is still pretty hard. And I'm not telling you, this is a semi-log plot, I'm not telling you how many cycles are on there, so I'm not giving you an indication, but each cycle is 10 times in the semi-log plot, so it's huge spikes to the side and nothing in the front. So we had a clean sheet of paper with a new constraint, stealth. So if you look at wing platform options, we had delta wings, straight wings, aft swept wings, forward swept wings. If you look at wing position, we had low wing, high wing, and anywhere in between. If you look at horizontal stabilizer, we had flying wings, wing body tail, wing body canard, 3 surface. If you look at inlet locations, we had under the nose, over the nose, on the side inlet. And the problem there is we knew what our fuselage was. It was an air fuselage with an engine at the back, lift fan behind the pilot, pilot in the front. But we didn't know what the wing platform, stabilizer, and all the rest of it looked like. But if we pick one of the 4 wing platforms, we then have 4 options for the stabilizer, 4 options for the inlet. It's not possible to do a trade study in all those combinations. So what we had to do was generate expert opinion. So I got experts from the Skunk Works to come in, and we had a scale system, must have, supersonic STOVL for the Marines, important to have, affordable, reliable, accessible, and nice to have, comfortable, you know, etc. And we had them all rated. Now, for me as the chief engineer, that was a good exercise because I got all of the different opinions, but it wasn't a very good team building exercise. The guys would argue with each other whether it ought to be a 2 or a 3. One guy would say, I'm going to bring my department head in to tell you why it has to be a 2. I said, he's not clear to the program, you can't do that. So he would storm out when we decided to rate it a 3. But I did get the information I needed, and the one issue that we couldn't settle on was the delta wing versus the aft swept wing, like the F-117. And so stereolithography was a new technology at the time. It was invented by a company in Northern California, or Southern California, about 20 miles from our plant. So we bought one of the first stereolithography machines, built a model with a delta wing and the aft swept wing, tested them in the radar range and the wind tunnel, and decided to go with the delta wing. So that was our initial platform. 3 surface, but the V-tails, so that we had the horizontal and vertical stabilizers in the form of a V-tail. Okay, so that was our airplane. We had to size it on the missions. There were 3 missions: deck launch intercept. So you're on the beach, you get word that the enemy fighters are coming, you need to climb to altitude and intercept them before they can get to the beach. Combat air patrol, which is very similar except you're loitering over the beach, you know they're coming, and you have to dash out to intercept them. And then close air support. And they had different requirements. So for deck launch intercept, you need high sweep and a high thrust to weight ratio. For loiter, you need low sweep, low thrust to weight ratio. For close air support, you need high sweep for a stable platform, high wing loading, And the way we resolved those was here to make a plot of thrust-to-weight ratio versus wing loading. So you can see for sustained Gs, you need a big wing with a low wing loading. For high speed, you need a small wing, like an F-104. And the compromise is somewhere in between. And we thought by putting a lot of requirements on the maneuver performance, we would drive the thrust-to-weight ratio sufficiently high to reach the 20% margin you'd like for hover in a VTOL airplane. But that drove the cost up, so we settled on some intermediate values. And that was our STOVL strike fighter, the Ghost Hawk, we called it. And the Marines loved it, but they were trying to develop the V-22 at the same time because they needed a transport airplane to resupply this airplane on the beach with ammo and fuel and so forth. And Cheney was Secretary of Defense, and he canceled it for the second time. So the Marines came to us and said, we like your concept a lot, but we got to get V-22 in service. We're a small service. We can only focus on one program at a time, so we'll get back to you. Well, it took 15 years to get the V-22 in service. They'd be getting back to us about now, I guess. The other problem was the Navy wanted their own stealthy Silver Bullet. It didn't make sense. The Navy said we can be on site quicker because we're deployed around the world, but we need the F-117s to come in to take down the SAM site so we can operate our F-18s. And the F-117s don't operate off the carriers, so they needed something stealthy that they could put on the carrier. They had an A-12 program which ran into weight problems, cost problems, and everybody went to what they called the AFX program, which was an attempt to design a stealthy bomber for the Navy, but they really had the F-18EF in mind. They just wanted to know if there was something else out there. So all our guys went off as stealth consultants on all the teams, and we were out of business. But fortunately, fate works for your advantage sometimes. General Molnar took over as chief head of requirements for Air Combat Command in the Air Force, and it's one of the first things he wanted to do in his new position was tour industry. And so he wanted to come to the Skunk Works for a day, and we have a small business and small number of programs. We didn't have enough to keep him occupied for a day. So Jack Gordon said, why don't you tell him about your STOVL strike fighter? And I'd been in the Air Force, and I knew that the Air Force wouldn't want to hear about a STOVL strike fighter because the Congress would say, well, the F-22 isn't STOVL, and you say you need STOVL, so we're going to cancel the F-22 program. But it occurred to me if I took out the lift system and put in a conventional nozzle and replace the lift fan with the fuel tank, I would have a single engine replacement for the F-16, which would be affordable and less expensive than the F-15. It could work with them as a strike fighter the same way the F-16 and the F-15 work together. So this was my last chart, and I said, sir, in addition to your Air Force conventional takeoff and landing variant, we have looked at a VTOL variant, and the Marines don't have the money. We know you're focused on the F-22, you don't have the money, but maybe you could have a joint program to investigate this feasibility. So they had some meetings in the Pentagon that I wasn't access to, and decided to come out with a proposal for a common strike fighter. And this is the point where the program came out of the black and into the blue. So it was opened up to everybody, and a lot of people say this was the start of the program, but it wasn't really. It had gone on for a while before. So the challenge was to design an Air Force Marine Corps common strike fighter, design a flight demonstrator aircraft based on the production aircraft, to validate a lift system concept, show that you had control of hot gas ingestion, which was a classic problem on VTOL airplanes, and to demonstrate conversion from hover to flight in a single mission. We call that Mission X. So we had, in the Skunk Works, when you don't have a program, you don't have a program area, you don't have any place to keep your documents, we had to shred everything we had. But when we had 90 days to respond to this RFP, so we looked at the F-22, which was similar in a lot of respects to the Joint Strike Fighter, the Ghost Hawk, except they had tails and we had canards. The reason they had tails was because the Russians were demonstrating the Cobra maneuver, which involved the airplane pitching up. The guy on your six would overshoot you. You'd drop down and get him. But it's strictly a bar bet kind of thing. Colonel Boyd, who was a very famous fighter pilot, developed the whole concept of energy maneuverability, came up with the Hail Mary concept in the Iraq War. Used to go to an air base, go to the bar, find some lieutenant, say, I can let you get behind me on my year 6, and in 60 seconds I'll be on year 6. He said, I'll take that bet. So they go up the next day, he could get on the 6, he'd pitch up, the guy would overshoot, he'd drop down, he'd be on his, but it's strictly air show, because the guy's wingman would shoot you down, because you lost all the speed. So it was good for bar bets, but not essential. We had the canards, they had the F-22 with the tails, so we had to switch to tails. And that became our proposal airplane. The Stovall variant had the lift system in it, and the CTOL variant had a lift tank instead of the lift fan. And we were viewed as a high-risk, high-payoff alternative. These were our 3 variants, Air Force F-35A, and I used the mnemonic, we invented it after the fact. A for airfield, that's the Air Force variant. B for beach, that's the Marine Corps variant. And C for carrier, that's the Navy variant. And you can see that the Air Force and Marine variants are basically the same externally. The difference is in the lift system. But the Navy variant, in order to get onto the carrier at slower speed and have the same control power, needed bigger flaps and slats and tails. And so I propose that we just extend the wing box with bigger flaps and slats and replace the tails. So that's what you saw inside, outside, and here's the basic 3 variants. You have a core airframe. You put in the small flaps and slats and tails for the Air Force variant. You put in the lift system for the Marine variant, and you put in the bigger flaps and slats and tails for the Navy variant. On the inside, we had a difference based on the F-16 experience. The F-16 would be sold to different companies and countries, and they would want some of their own equipment in there. So the Israelis, for example, wanted their own ejection seat rather than the Martin Baker seat. So they call those cousin parts, and we use cousin parts. So for example, the bulkhead that takes the main landing gear loads in the Air Force and Marine airplanes, it's 10 feet per second. So the airplane's coming in at 180 knots or something, but its vertical descent velocity is 10 feet per second. The Navy requirement is 25 feet per second, because the ship may be pitching up when you're coming down. You don't want to break the airplane. So it would be titanium and nominally 3/4 of an inch thick, and the Air Force and Marine variant would be aluminum and nominally a 1/2 inch thick, but they'd fit into the structure in the same location. So we took our airplane to NASA, tested it in the hover rig facility at various heights, at various pitch, roll, and yaw angles, showed that you didn't have a hot gas ingestion problem, put it in the 80 by 120 tunnel, showed that it could go through transition from hover to flight speed, and became the low-risk, high-payoff alternative. This was the Boeing McDonnell Douglas concept. They took some of the gas from the rear engine, took it forward to drive the lift fan, and otherwise a similar canard V-tail configuration. But when they built their propulsion system, they found that they couldn't get the lift fan to spin up fast enough, so they had to run pitch pipes forward to augment the flow. Also, they had hot gases in the lift fan, even though it is a fan because of the hot gases they used to drive it. So they had hot gas ingestion problem. They need lift shield jets to keep the hot gases from getting into the airplane. Anyway, they had something like 19 nozzles on the airplane. And they said, this isn't going to work. We're going to switch to lift engines. And the Marines said, don't do that. The Russians have tried lift engines. They're terrible. We're a small service. We can't have 2 engines, 2 sets of tools, 2 logistics tails, 2 mechanics, 2 test stands on the small carriers. Don't do that. And McDonnell Douglas made a big mistake. They said, well, they're going to love, the Air Force and the Navy are going to love our conventional variants like the F-4 Phantom, and the Marines are just going to have to live with the lift engines. Big mistake. There was a third competitor, Boeing. They had proposed a Harrier-like concept with 2 lift jets under the CG, and they were viewed as low risk. And the congressman from Boeing, Norm Dix, went to Congress, convinced enough of his colleagues that you've got 2 high-risk new concepts here. You need something that will work. We know the Harrier works. You need Boeing in the competition. So Boeing put up $10 million of their money. Congress put up another $10 million, so they had the same $20 million we had, that is McDonnell Douglas and Lockheed. And they were the third competitor. And the next time I was in Washington, I said, this doesn't seem fair. We had a competition, we won and they lost, and they're now back in it. They said, son, you don't understand. This is what's so great about America. If mommy says no, you can always go to daddy. And the congressman's job is to represent his constituents. So Norm Dix was doing what he was supposed to do. He was making Boeing's case in Congress. He made their case, and they're the third competitor. They weren't part of the original program, so they didn't have time scheduled at NASA Ames. They had to build their own hover rig, but they didn't get into a wind tunnel, full-size wind tunnel, and they were viewed as moderate risk and a low payoff. And when the winners were announced, it was Lockheed and Boeing. You don't want to mess with the Marines. Heck with San Juan Hill. They're terrific on Capitol Hill. And so when they said they were going with lift engines, they were out and Boeing was in. And in fact, they had an agreement between Boeing and McDonnell Douglas that whoever won would sell their company to the winner. So McDonnell Douglas was sold to Boeing, and that's how that happened. So we were doing a demonstrator. We were going to build 2 airframes, but demonstrate all 3 variants. We wanted to fly production configurations, and we were confident, because we were just ripping off the F-22, that it would work. But we wanted to demonstrate stall performance and supersonic speeds for the Marines and improve the handling qualities and carrier suitability for the Navy, because we'd never built a Navy airplane before. So we took the same basic approach. We had 2 airframes, no avionics, but Navy structure in them to take up the weight of the avionics. We flew it first as an Air Force variant with the conventional smaller wings, flaps, slats, and tails. And then we put the lift engine into it to turn it into the Marine variant. The other airplane we devoted to the Navy variant with the larger flaps, slats, and tail surfaces. But if one of the other 2 airplanes had crashed, we could have completed the program with the 1 remaining airframe. So the Marines were concerned that this airplane, which is twice as big as the Harrier, wouldn't be able to land on concrete. And so we did a multi-physics simulation showing that the airplane could land on concrete okay. Concrete spalls at 1,000 degrees Fahrenheit. So we put Tom Morgenfeld, our chief test pilot, into the simulator. He did a vertical landing. We took his data and then did the CFD simulation, showed that it only got to 600 degrees and we were okay. And forgot about the problem. Now the interesting thing is when Pratt & Whitney was testing our engine, they tested 2 nozzles, like a straight aft nozzle and an elbow nozzle. And of course they ran for more than 15 seconds, and so they spalled the concrete. They threw huge chunks of concrete into the employee parking lot, broke car windows and hoods and so forth. So they turned the nozzle upside down. But it shows what can happen. You solve your problem, you forget about it, and then it comes back to bite you. We used avatars to show that you could get in and perform some service tasks. So here's a guy performing some service in the weapons bay. We used to build iron birds where we'd lay out the hydraulics and the electrics on a frame representing the airplane and test them. In our case, we used the airplanes, the X-planes, as the iron birds. We also used the flight simulator, moving base simulator that we had built for the F-22 program. And the 2 major things we worked on it were the stick. So the Marine pilots wanted 3 inceptors, so a stick, a throttle, and a nozzle lever. And the software engineers said, well, we can put the nozzle lever into the stick. You pull back the stick part way, you get flaps. You pull it back the rest of the way, you get nozzle vectoring. And they had quite an argument about it. They decided to go with the 2 inceptor. Marine pilot quit the program in disgust. The other thing we did was qualified the airplane for air-to-air refueling in the simulator. And that turned out to be a huge advantage for us. We were only building 2 airplanes, so we used stereolith to build models of some of the parts. So for example, there were mom and pop shops in the area that could build some parts cheaper than we could, but they didn't have 3D CATIA systems. So we built a model part for them and gave them the dimensions, and they had something to work with. One of the labor-intensive things is ducts and tubes. The guy has to take a tube, estimate how much it needs to be bent, go to the bending machine, bend it, take it to the airplane, see if he bent it enough or too much, go back and rebend it or unbend it. Eventually, when he gets the part done, he'll mark it on the pegboard. They'll bend up the production piece and put it in the airplane. We built a stereolith model and just gave them that. They put it in the pegboard, went right to the airplane, and it fit. This was a 3D CATIA model showing different materials in different colors. And I said, look, we've got a 3D CATIA model. Why generate 2D blueprints? Why don't we put this down on the shop floor and give it to the guys and let them use that to put the airplane together? And the customer said, don't do that. You guys put airplanes together the same way you do puzzles. You give them a bunch of pieces and you give them a picture and said, put it together so it looks like that. Figure out with your computers how they should put it together. There's a intermediate fuselage, kind of an interesting part because it's where the two ducts come together and join into one, feeding the inlet. And so there's one inlet duct and there's parts. Now this is running fast time for our purposes, but the guys could go down and stop and start it, look up the part number, what sequence to put it together in. That's the shaft hole in the middle there between the two ducts. Okay, it runs on and I'll just stop it here. So Boeing actually started their flight test program 30 days before ours, but they had no air-to-air refueling. They tried to use a Navy drogue system, and their wide airplane would push the drogue away as they tried to get it into the receptacle on the airplane. So they had to come down, and when you come down after an hour's flight, there's always squawks you got to take care of before you can go back up again. But we could go up, we could refuel, which we qualified in the simulator using an Air Force refueling system, piggybacking off the F-22 tankers that were in orbit supporting that flight test program. And we completed our flight test program in 30 days, same time they finished theirs. And General Mike Howe, who was the Marine Corps program manager at the time, was rotated between Air Force, Navy, and Marine, the program manager, the exec, and the chief engineer. And he said people were stunned. And we also did something else that they don't usually do. We had our pilots fly the airplane usually and then brief the Marine and Navy pilots about how great it was. We had their pilots in the system and flying our airplane firsthand as part of the test squadron. Here's a picture of the conversion of the conventional variant to the Stovall variant by dropping the lift fan into that cavity behind the cockpit. Here's just an interesting IR picture showing what we demonstrated at NASA Ames. White is hot, so you see the hot jets. There's a cold lift fan in front of it. You don't see that, but it comes together, produces a wall that keeps the hot gases from being ingested into the airplane. So when we went to fly Mission X, which was the first time anybody who would take a short takeoff, go supersonic, and land vertically, we had Major Art Tomasetti, Turbo, fly that mission. And so he's the first person who flew a supersonic Stovall mission. Boeing couldn't do that mission. They had to take, well, I'll show you that later. Anyway, here's the Navy variant over the Naval Academy. Now, Tom Morgenfeld, our chief test pilot, was a graduate of the Academy. His roommate was now commandant. He told him, have the midshipmen in formation at 100 hours, tell them to look up. They'll see something cool. So he flew over there, and that's 150 miles north of Patuxent River, where we were doing our Navy test. So the phones started ringing off the hooks in California and Texas and Pax River. What's Tom doing up there? And he said he got lost. So that's why I have a distribution statement up there. It's okay to say that he got lost and he was over the Academy. It was also the first X-plane to fly across the U.S. It made 2 flights. It stopped in Texas, so the guys there working on the airplane and would be building the production version got to see it, and then it flew on to Pax River. Okay, so this is the A variant taking off. And even though it was only 40 miles from our plant to Edwards Air Force Base where we were doing flight tests, Boeing had flown over and had trouble with our hydraulics and couldn't lower their gear, retract their gear. So we made a point of retracting our gear. We demonstrated the full flight envelope. This is the Navy variant. There it is over Pax River, practicing bolters. So it's coming down on the deck, pretends it missed the cable and had to take off again right away. And the Navy said, this airplane's ready to go on the ship. And then here's the VSTOL variant. The nozzle vector's down, and it takes off like on a hydraulic lift. We wanted to show that it could go supersonic, so you clean it up. Oh, watch the nozzle at the rear. It vectors down, and the airplane's off in 300 feet. Here it is going supersonic. And if you've been to some of the air shows, you know the Marines do a great job on air shows. We wanted to show that they could continue to do that. So here they're looking at the crowd. They bow to the crowd. And they wanted to show that we could land on the same aluminum plates that they staked down in the desert and on the beach. And we showed that the airplane could do that. There we go. So Boeing had taken a direct lift approach. They had a smaller mass flow at a higher velocity and only 32,000 pounds of thrust. And in vertical mode, they had to take off the landing gear doors, the translating hood on the inlets, these slats. I think the pilot was in his underwear, and they were barely able to fly. We had 40,000 pounds of thrust, which was plenty thrust to bring back the high-value weapons. You didn't have to drop them on some cow or in the ocean on the way back to the ship. And so Boeing was very professional. They credited Lockheed with the win because of the very innovative lift fan. Aviation Week also said the lift fan put us over the top. And Interavia, which is a British version, European version of Aviation Week, also credited the lift fan. And we were awarded the Collier Trophy in the following year for the lift fan propulsion system, which is given for the greatest achievement in aeronautics or astronautics in America, demonstrated during the preceding year. But there's other factors involved. Pilots like to look good on the ramp. And here's the two airplanes side by side. We were in the two hangars there and behind them. You can see the tower in the background. There were speakers hanging in the hangars. We could hear the chatter in the tower. And when they started calling the Boeing airplane Monica after Monica Lewinsky, I think because it's kind of chubby looking, we knew we had won the beauty contest. I'm going to touch a little bit on what's happened. If you guys are so smart, how come your airplane's so late and over budget? And actually what happened was we got new requirements laid onto the airplane after it was designed and built. The Air Force came in and said, 7.5 Gs, you can't have a fighter with 7.5 Gs, you need 9 Gs, and you need a gun. So we had to redesign the structure to go from 7.5 Gs to 9 Gs. They said it can't carry anything except weapons in the weapons bay. After you've taken down the SAM sites, you want to join the rest of the airplanes as a bomb truck. So you need pylons on there, including carrying the Mark 84 2,000-pound bomb. And the two biggest ones were the helmet display. No pilot ever said, I need to look through the floor. But a lot of people with IRAD projects said, this is going to be the last manned airplane. If I don't get my gimmick on this airplane, it's never going to fly. So they made the case, and we had a lot of stuff on the airplane that wasn't really necessary. And then, of course, software is the other challenge. The F-16 had like 250,000 lines of code for the fly-by-wire system. The JSF has 5 million. The F-22 has 5 million. The JSF is headed to 20 million. And the software engineers can make more money working for Pixar and game companies, so it's hard to get software engineers to work for us, and that's been another holdup. But the airplane is a better airplane than it would have been because it has now mode stealth mode, which is the original airplane, and what we're calling beast mode, which is the bomb truck. This is the current status of the program, and actually this is a little bit out of date. It's now like 1250 airplanes in service, and they're distributed. These are my numbers based on what I've read. There's no published list, but mostly A's, B's, and a few C's. There are now 2 squadrons based here in San Diego, actually, on the carriers. They're working on the 3rd squadron. So 2 squadrons is 100, probably 150 or so now working on the 3rd squadron. So I don't want to give the impression that this was a Lockheed effort entirely. We were teamed with Northrop Grumman and BAE Systems on the airframe. Rolls-Royce and Pratt & Whitney were teamed on the propulsion system, Open Kimono. But the real key was the program office. On the F-111 program, which was the other attempt to do a joint program, they had a Navy program office and an Air Force program office, and the poor contractor was stuck between them, had to resolve the conflicts. They had a common program office, rotated the leadership like we did, and called themselves Purple Shooters and gave us one set of requirements, which made our life a whole lot easier. Okay, well, thank you for coming.